Hi, Paul. You're on the video recording now. Alright, so taking a look at a linear system, I just mentioned that earlier, is a linear system is a set of two or more linear equations. So we take a look at the linear equations given to us. Which of these do you think will be a linear system? You got 1, 2, 3, 4 choices. Do you think the first one is a linear system? Do you think the first one is made up of two linear equations? Yes or no? Yes, they're both linear equations. They're just in general form or standard form. Yay, our first cell phone going off on the video. Thanks, Paul. Alright, first one is a system of linear equations. Right? Both those are linear equations. What about the second one? Are those two linear equations? How can we be sure they're linear equations? Well, they're x and y variables. They're all degree 1, right? So they're all power of 1. There's no squared or cubes or anything in there. Only difference is that we've got a fraction in there. It doesn't really deter anything. It's still a set of linear equations. What about the third one? Is that a set of linear equations? No. One of them is a linear equation. The other one is not. The other one's a quadratic equation. It's got a power 2. So this one is not a system of linear equations. And what about the last one? Is that a set of linear equations? Yes, it is. So linear system. So those three are linear systems. They are linear systems because they have equations that are linear equations in them. So as I mentioned earlier, a solution to any linear system is going to be the point xy that satisfies the equation. That means this point must satisfy both equations in order to be a solution for the entire system. So if you were going to draw them, then this is the point where both of those lines would intersect. So first things first, I'm telling you that there are these two lines in a system. I want to check to see if the point 2, 3 would be a solution for the system. So when I'm asked to check to see if that's a solution, I'm just going to go ahead and take point 2, 3. I'm going to plug it into each of those equations. And if the left hand side equals right hand side match up for each one of them, then I know that it's satisfying each of those equations. So let's do that. So I want to verify the system below has a solution of x equals 2, y equals 3. I'll start off with equation number 1. So I'll say check 1. So I'm going to plug that point in. Okay, substitute. Actually, it's already saying that up there. Substitute. So we're going to substitute 2, 3 into each equation. So x is 2, y is 3. So let's see what happens. 2 take away 3 is supposed to equal -1. And then -1 equals -1. So it does verify there. Left hand side equals right hand side. I do the same thing with equation number 2. So I'm going to check 2. So 2 times 2 plus 3 times 3 has to equal 10. 2 times 2 is 4 plus 3 times 3 is 9 equals 10. 13 equals 10. Is that statement true? 13 equals 10? No, it's a false statement. So it doesn't satisfy that second equation. So I'll say since 2, 3 does not satisfy the second equation, two, 3 is not a solution of the system. Again, if it has to be a solution of the system, it's got to satisfy all the equations in that system. Whether that's one equation, two equations, three or four. It's got to satisfy all of them. Can't just satisfy some and not the other. Alright, next up, we're going to create some of these systems using word problems. So here are some of the steps we're going to use. The ability to translate words or phrases into the language of mathematics is an important skill. One use of such skill is to create a system of linear equations. So whenever we're creating a linear equation or a linear system, we're going to first use a let statement, right? So let, for example, let the cost of each item equal x, right? That's a let statement. So anytime you're solving a word problem, you want to first start off with the let statement. A let statement is defining a variable. It's telling you when you say the variable x, well, what does x really represent? Okay, what does x mean? Then to develop a model of linear equations, we must use the equation to find out what is being looked for, right? So we did that when we wrote the let statement. We assign variables to these figures, so whatever we're missing, we assign it a variable, either x or y. We organize the information given in the question and formulate the equations to make a linear system. We're then going to go ahead and graph each linear system on a grid and find the intersection point. And then lastly, just to make sure we've got the right answer, we're going to substitute the intersection point into each equation to check. We're going to do this last step just to make sure that we haven't read the wrong point or we haven't graphed the wrong way. So for the purpose of this section, we're going to focus on items 1 and 2, just coming up with the equation. So let's take a look at our first example. Okay, so the perimeter of Nunavut flag is 16 feet. Its length is 2 feet longer than its width. So we're given some information. We're told what the perimeter is, we're told what the length is, and both of those are in relation to the width. So one of the things that we're missing is the width of that flag. So the first thing that I'm going to do is I'm going to go ahead and write a let statement. I'm going to say let the width of the flag equals x. Actually, I'll be w. I'll make it a variable w just to be consistent. Width equals w. So say let the width of the flag be w. So now that I know what the width is, the question is telling me its length. Therefore, the length is 2 feet longer than its width. So what's going to be the expression for that? The length is 2 feet longer than the width. 2 feet longer than the width. W plus 2. Right, so instead of using length, I'm just going to assign it a variable. L equals W plus 2. And I haven't defined L, so I got to define that as well. So I'll say let the length of the flag be represented by the variable L. Each variable that I use, I've got to know what that variable represents. Shouldn't just go straight to X, W, A, B, C. You've got to define what they mean. So now that I know that L represents length, W represents width, so one of the expressions that I get is L equals W plus 2. There's another expression that I can generate from that statement. It's telling me that the perimeter of a Nunavut flag is 16 feet. How can I convert that information into an equation? What does the perimeter represent? Speak up a little bit. Not the area. The length all the way around a shape. Right? In this case, our flag is a rectangular shape. So what's going to be the length all the way around the flag? It's 16 feet, but what does it represent in terms of an expression?
The perimeter?
The perimeter, what's the formula for a perimeter? What's the expression for a perimeter? Right? Think of it this way. Length, width, length, width.
2L plus 2W.
That's right. So 2L, 2 times the length, plus 2 times the width equals 16. 2 times the length plus 2 times the width equals 16. So here is a system of equations. I've got equation number 1. Actually, I'll just move this down so it's a little bit more visible. I've got equation number 1 here. And I've got equation number 2. This is a system of linear equations. System of linear equations. Alright, so Denise has determined that the no-limit flag is going to be 5 feet long and 3 feet wide. Use the linear system from part A to verify that Denise is correct. So we want to check to see if Denise is correct. So we're going to go ahead and check our work. So I'll first label these. I'll call this 1 and I'll call this 2. So I'm going to say check 1. Check equation number 1. What Denise is saying is that its length is 5, so L equals 5, and W is 3. I want to check to see if Denise is correct. Denise is going to be correct if we satisfy both of those equations. So first equation, L has to be, so 5 has to equal 3 plus 2, which means 5 has to equal 5. It checks. Secondly, I want to check equation number 2. Equation number 2 says 2 times the length, so 2 times 5, plus 2 times the width, so 2 times 3, has to equal 16. 2 times 5 is 10, plus 2 times 3 is 6, has to equal 16. 16 has to equal 16. That checks. Right, so since both equations check, we can verify we verified that Denise is correct. Right, so we're coming up with a couple of linear equations from the problem. Notice this time we're using 2 different variables. We're not just combining them into a single equation. We're writing 2 separate equations to make a system, and then all we're doing is setting up a system and then verifying if something is a solution. How we're going to go ahead and algebraically solve that system is going to come in the next lesson. Okay, let's have you try example number 2. See what you come up with.